In this video, I will derive the discrete trigonometric expression of the Fourier transform. A f function of x can be expanded into an infinite series of cosine and sine functions like this. A sub n is the coefficient of cosine functions, b sub n is the coefficient of the sine functions, n is from 1 to infinity, n is an integer, and in front of this series we have 1/2 times a naught. There's a reason for this 1/2. You'll see that later. If we integrate both sides from negative pi to pi, we will get the expression of a naught. So let's do this. We integrate both sides from negative pi to pi, and then over here the integral of cosine nx is sine nx over n. The integral of sine nx is negative cosine nx over n. If you look at this function, it's 0 because sine n pi and sine negative n pi are both zeros. And over here, this integral value is also 0 because cosine functions are even functions. So if you have cosine n pi, it equals cosine negative n pi. Therefore, if you plug in the lower limits and upper limit, you get the same value. They cancel, and then therefore this entire infinite series equals 0. And then we have only one non-zero term, which is here, and then you have a naught equals 1 over pi times the integral of fx from negative pi to pi. So now we determined the expression of a naught. Now let's determine the expression of a sub n. We'll use a trick here. This is the infinite series of an arbitrary function fx. Now we multiply both sides by cosine mx followed by integration from negative pi to pi. And then we have this equation here. Looks complicated, but first this part equals 0. There's a reason. The integral of cosine mx is sine mx over m, and then you plug in negative pi and pi, you get 0. So this part disappears. Now we have this integral equals the infinite series of the sum of these two integrals, one in red, one in blue. And then we will prove this. If n is different from m, this integral is 0. This integral is also 0. Therefore, n must be equal to m for this term to be a non-zero term. So first, let's look at this situation when n is different from m. When that's the case, the product of two cosine functions can be expressed as the sum of two different cosine functions over 2. Now we integrate these two cosine functions, and then we plug in the lower and the upper limits. We know sine n pi is 0, sine n minus m pi is also 0. Anyway, the sine function of a integer multiple of pi is 0. Therefore, we have 0 minus 0 here, and also we have 0 minus 0 here. Therefore, this integral in red is 0 if n is different from m. Again, if n is different from m, the product of a sine function and a cosine function can be expressed as the difference between two other sine functions, and then we integrate these two sine functions here and here. Now we plug in pi and negative pi because cosine functions are even functions. Therefore, it doesn't matter if you plug in x equals pi here or x equals negative pi here. You get the same value for the cosine function, therefore they cancel. Over here you get 0, and this part is also 0. So we just proved that if n is different from m, these two integrals are zeros. Therefore, this entire infinite series is reduced to only two possibly non-zero terms, which is a sub m times the integral of cosine mx squared, and this is bn cosine mx times sine mx. All right, let's look at this. When n is equal to m, and then we can actually have this term being expressed as cosine x squared or cosine mx squared, and then we can integrate this, we get pi, and we can also integrate this sine nx cosine nx, which is just sine 2x over 2. We integrate this. We can easily obtain this 0 here, because again, the integral of this guy is actually cosine 2nx divided by negative 4n. And because this cosine function is an even function, if you plug in negative pi or pi into this cosine function, you get the same value. Therefore, the lower limit and upper limit cancel, you get 0. And again, when n equals m, we have this integral in red to be non-zero, and this integral in blue happens to be 0 as well. Therefore, this entire infinite series over here contains only one non-zero term. That is when n equals m. This integral is non-zero. Alright, since we have only one non-zero term, again, we just write out that non-zero term, which is a sub m times pi. We get this equation here. Now we determined the expression of a sub m, which is just 1 over pi times the integral of fx times cosine mx times dx. Now you know why we put a half here, because when we put this 1/2 in front of a naught, this expression applies to a naught as well. You can plug in m equals 0, and then you'll just simply integrate this fx from negative pi to pi, and then this integral divided by pi, you have a sub 0. And we got that expression here. A sub 0 is 1 over pi times the integral of fx from negative pi to pi. Again, we put this 1/2 here to make this a sub 0 and all other a sub n to have a consistent formula. And what formula? Again, this is the formula for a sub 0 and other a sub m or a sub n, so over here. All right, now let's determine the expression of b sub n by first multiplying both sides by sine mx, and then followed by integration. We have this expression here. So first, let's integrate this part. This part is 0 because the integral of sine mx is negative cosine mx over m. And then cosine functions are even functions. So if you plug in negative pi or pi, you get the same value for that cosine function. So therefore, this integral is 0. Then we have two other integrals to evaluate, one in red, one in blue. Again, we'll prove this. If n is different from m, this integral is 0. Actually, this one is 0 as well. Again, that will reduce this infinite series into only two terms, possibly non-zero terms. So first, let's plug in this. If n is different from m, the product of cosine and sine functions can be written into the sum of two different sine functions over 2. We integrate both sides, we get cosine functions. Again, cosine functions are even functions. So if you plug in negative pi or pi into the cosine function, the value is the same. Therefore, this integral value is 0. This one is 0. Overall, the result is 0 for this integral in red if n is different from m. Again, if n is different from m, the product of two sine functions is this cosine function minus this cosine function. And then we integrate these two cosine functions, we get sine functions. And sine functions are zeros when you're taking the sine functions of an infinite multiple of pi or negative pi. Therefore, this is 0 minus 0. This part is 0 minus 0. Well, you get 0. Therefore, we eliminated all other terms except when n is equal to m. So now when n is equal to m, we integrate this part. We learn that this is again 0. And if we integrate this part, this is actually sine nx squared, which is 1 minus cosine 2nx over 2. If we integrate this, well, this part becomes 0 because the integral of this part is a sine function. Again, a sine function of the integer multiple of pi or negative pi is 0. Therefore, we just integrate 1/2 dx, which is just pi if you plug in the lower limit and the upper limit. So again, if you look at this entire series here, really complicated, but this is 0. All of this is 0, and among this infinite number of terms, there's only one 0 term, which is b sub m times pi. Therefore, we determined the expression of b sub m, which is 1 over pi times the integral of fx times sine mx dx. So overall, we determined the expression of a sub n and b sub n. I said n, not m, because anyway n and m are dummy variables. So therefore, we have now the discrete trigonometric expression of the Fourier transform. This over here in bold font. Fx, any fx, can be expressed as 1/2 a naught plus this infinite series is from 1 to infinity, and then we have an times cosine nx plus bn times sine nx. And what about the expressions of a sub n and b sub n? A sub n adopts this form, b sub n adopts this form. What's the difference over here? Over here, this is fx times cosine nx, this is fx times sine nx. And this equation applies to a sub 0 case. Again, a sub 0 is simply 1 over pi times this integral times fx times 1. Cosine 0x is 1 dx. So this is the reason we put 1/2 here to make this a0 and an consistent. Now we will verify this infinite series by verifying by using 3 different examples. We'll use sine x, cosine 2x, and x as the expression of fx, and see if we can obtain this a sub n and b sub n, and then if we can verify the left-hand side equals the right-hand side. Now let's look at the first example. If fx equals sine x, and then we look at a sub n is 1 over pi times the integral of fx, now fx is sine x, times cosine nx dx. If you integrate this, I guarantee you the value is 0 if you are integrating a odd function from negative L to positive L, where if L is just any constant. The reason is simple. If you integrate an odd function, the integral value on the left-hand side of the x equals 0 axis and the integral value of the right half are exactly the same, but with opposite signs. Therefore, they cancel. So we know this a sub n equals 0 here. How about b sub n? Again, we just plug in this fx here. This is your fx times sine nx. And the product of two sine functions can be expressed as the difference between these two cosine functions divided by 2. And if n equals 1, this part becomes 1, and then we integrate this part. The result is 1, so b sub 1 is 1. If n is different from 1, again, we just integrate these two cosine functions, get two sine functions. Again, the sine function of an integer multiple of pi is 0. So over here we have 0 minus 0, and this part is 0 minus 0 as well. Therefore, we have just 0. We just proved that a sub n is always 0. And how about b sub n? Only b sub 1 is 1, and b sub n is 0 in case this n is different from 1. Sorry about this mistake here. So therefore, we learned that in this infinite series, there's only one non-zero term, which is just b sub 1 times sine 1 sub x, which happens to be sine x. And we just verify this fx equals sine x. Now example 2, fx equals cosine 2x. So really, for this example, we expect to see a2 is 1, and a sub n, if n is different from 2, is 0, and b sub n is always 0. So let's look at b sub n. b sub n is 1 over pi times the integral of cosine 2 pi times sine nx. Again, this is an even function, this is an odd function, so the product is an odd function. And again, the integral of an odd function is always 0 if you have this lower limit and upper limit to be opposite to each other. Again, this is just because the integral value of the left half and the integral value of the right half cancel. Now let's look at a sub n. We need to integrate the product of two cosine functions, which is just the sum of just two other cosine functions, n plus 2, n minus 2, and then divided by 2. So we have two different situations. If n equals 2, this part becomes 1, and then we integrate this, the result is 1. Why? Because the integral of cosine 4x is sine 4x over 4, and sine 4 pi is 0, cosine or sine negative 4 pi is also 0. And the integral of 1/2 dx is simply 1/2 x. From negative pi to pi, you get pi. Pi divided by pi, you get 1. So we just proved this a2 equals 1. What if n is different from 2? We just need to integrate this two cosine function. We will get sine functions. And again, this is 0, this is 0. Therefore, among this infinite number of terms, there's only one non-zero term, which is just a2 times cosine 2x. And a2 is 1. Therefore, we proved this fx equals cosine 2x. Now the last example, fx equals x. This is a bit complicated. First, let's look at a sub n. Now let's look at this integral. Again, x is an odd function, cosine x is even function, the product is an odd function, and again, the integral value of an odd function from negative L to positive L, regardless of the value of L, is going to be 0. How about b sub n? We're going to integrate this, and we're going to have to use some tricks. The integral of sine nx is cosine nx divided by negative n, so we have negative 1 over n here, and then we have this d cosine nx here. Now we're going to use the product rule in differential calculus, which is f dg equals dfg minus gdf. So this is your f, this is a g, this is fg, this is f, this is g. So again, I'm just using f dg equals dfg minus gdf. All right, that's why I used the difference between these two integrals. The integral of the exact differential of function is itself, so I just need to plug in the value of x to be negative pi and pi, and then we have this is my upper limit, this is my lower limit. How about this guy? This guy is simply 0. The integral of cosine nx is sine nx over n, and again, sine n pi is 0, sine negative n pi is 0. Therefore, we have just these two terms, and these two terms do not cancel. We have this expression here. Negative 2 times cosine n pi over n. And cosine n pi can be 1 or negative 1. When n is an odd number, you get negative 1. When n is an even number, you get 1. Therefore, the expression can be expressed as 2 times negative 1 to the n plus 1 divided by n. Again, if you plug in a odd number here, and then you have 2 over n. If you plug in an even number here, you get negative 2 over n. All right. So therefore, x can be expanded into this infinite series of sine functions, and we can expand it. We have 2 times sine 1x over 1 minus sine 2x over 2 plus sine 3x over 3 minus sine 4x over 4 plus sine 5x over 5 minus sine 6x over 6, and so on. So you can plug in x equals 1/2 pi here on the left hand side, on the right hand side, and you can verify this part is approximately 1/2 of pi. So what I did is I used a Excel spreadsheet, which is also uploaded to the Google Drive for you to use, and I summed up the first 1,000 non-zero terms of this, and I got a number very, very close to 1/2 of pi. Why did I choose 1/2 of pi? Because, well, sine 1/2 of pi is just 1. And sine 2 times 1/2 of pi is 0, so this is 0, this is 0. All those even terms equal 0. And how about the odd terms? Odd terms, you have this one is 1 over 1. This part is negative 1 over 3, and then you have positive 1 over 5, negative 1 over 7, positive 1 over 9, negative 1 over 11. So that's why I used this 1/2 pi. So I'm going to show you the Excel spreadsheet over here. So this is what I did, and it's just 1, 3, 5, 7. Again, all those even terms become 0. And over here, I just evaluated 1 over 1, negative 1 over 3, 1 over 5, negative 1 over 7, 1 over 9. So you can see this is just 1 over 9. and this is just negative 1 over 11. And over here I summed up the first 1,000 terms from the second row to this 1,001 first row, and then I multiply everything by 2, and I got this actually very close to 1/2 of pi. How close? I'm using this divided by 1/2 of pi. We got this expression here, and we get 99.97% of 1/2 of pi here. All right, so you may use this Excel sheet as well to verify the result. All right, and get back to here again. So this thing times 2, this sum times 2 equals 1/2 of pi. Therefore, I'm actually providing you one way to approximate pi. Pi is just 4 times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9. So you can verify this yourself. You can get a very accurate value of pi by just doing this series.